Just one second.
Okay.
Let's just go ahead.
Yeah. You can go. You can start it now.
Welcome everybody to new webinar for the related to the Admire project. Today we have a webinar related to the GekkoFS system. You know that is developed in Mainz and also in cooperation with the Barcelona Supercomputing Center. So today we'll see how is the design, the installation, and the usage of the system. We'll have two speakers. First, we have Marc Andre Bev from Mainz, developing basically Gecko, and at the end we'll have Ramon No from BSc, that he will be showing an example of the usage of Gecko in Mare Nostrum. Okay, so thank you for the presentation, and remember, you have any question, please wait to the end of the session to do the questions. Okay, thank you, Marc and Ramon. I think you can start.
Okay, thanks, Jesus, for the introduction. Also, thank you, Barbara, for setting up the WebEx and sending out the invitation. So yeah, as Jesus said, I'm Marc, and Ramon and I will today talk about GekkoFS. I will start. Basically, I give a little bit of an agenda here because it's a little bit of a longer talk. So first, I will talk about just the history in general, about the publications that we have, and then we go into the motivation. What did we actually want to achieve with GekkoFS? And then what are our core challenges, and kind of what is GekkoFS at the moment, and what it will be in Admire as the project goes on. Then I will show some numbers, some success stories that we had, and then also just to get the bridge to Admire what our immediate next steps are within the project. And then I will give a quick demo on how to actually install the file system, and I will do this here on my local machine, and then also give a demo how it works and how you are using it, what the limitations are, what you need to look out basically. And then at the last point, Ramon will show a demo how to use it in a supercomputing environment. So first off, GekkoFS was actually created in the German-funded 8FS project, which was a German Research Foundation funded project. It started in 2016, and after some discussions, we started on the first commit in 2017. The BSc collaboration started in early 2018 within the EU-funded Next Gen project. I'm sorry, do you hear an echo right now? Okay.
Yes, ma'am.
Okay. Nefis, you have the audio on. Okay. So now, so next part, and then in 2019, after our publication, we ranked 4th in the IO 500, the No Challenge. I will talk about this a little bit later, but this is basically an effort of the storage community to be able to compare file systems on different systems. And then since 2017, it is funded by the Admire project, of course, but also by another German-funded project called Fidium. We have a number of publications here. Of course, the main publications are on Cluster 2018 and in the Journal of Computer Science and Technology in 2020. But then we also have other papers by GekkoFS, which was a collaboration where GekkoFS was used as a forwarding layer was added to GekkoFS, and this was published on the IPTPS conference last year. And then lastly, last year we also, again with the BSc collaboration, this was also Fred Schimmelpfennig is also in our teams, and here we were looking into deep learning and how it works with GekkoFS, and I'll also show that later how that went out. So first, for the motivation, how we started out with, we have these parallel file systems, GekkoFS, Lustre, and they are pretty old at this point, right? They have been designed almost or more than 2 decades ago at this point, and they have been optimized for the standard HPC workloads back in the day for the sequential access on large files. Nowadays we have other applications, and now it shifted a little bit, but again, these kind of files need to optimized for the generic use case so that every application actually runs with it as it would be on your local machine, right? This makes it very easy to develop applications. But what we have seen in the past year is that in HPC, we have new kind of applications where you suddenly process and analyze huge amounts of data, and we call these data-driven science applications. And they have also introduced new access patterns, which the parallel file system actually cannot work that well with. And these include, for instance, a lot of metadata operations, random access, small I/O requests. I'm sure you've seen that, where if you do that, the performance that you get from the parallel file system plummets oftentimes and also affects other users, right? So you have the interference as well. A single application can easily actually have an effect on other users. This is mostly, or a part of that reason is because the parallel file system is still using slow HDDs as their data backend. For metadata, they're usually using SSDs now because they're just a lot less nodes that are doing the metadata servers. But for the most part, the data servers are still HDDs. Of course, we have newer storage technologies, persistent memories, NVMe-based SSDs, but the price is still too high to use them on a big scope. So here's just an example from the Mare Nostrum supercomputer in Barcelona, where basically we have a specific workload, and we run this workload on different days, on different times. And what you see here is for read-write throughput, you have completely different bandwidth expectations, right? You get order of magnitudes different performance specifically for write. As you can see here, as you can see my mouse for 32 nodes. And this, of course, not only has an effect on the I/O throughput of your application, but also it makes it very difficult to kind of define how long your application should run, right? And the problem here is that you usually have to overestimate your job time, which then has inefficiencies in the sense that the job scheduler cannot properly schedule jobs because they finish all much earlier or not, depending on how fast the I/O system how fast the I/O system state at the moment is. So there's another thing that we have in a lot of supercomputers now is that we have node local storage on each node. And these are usually cheap SSDs. These are not usually NVMe SSDs. They're like SATA SSDs. And for instance, in Mare Nostrum 4, even though we have a very high peak I/O bandwidth of the parallel file system, right here on the left side, if you look at the number of nodes, then you actually have very little if every node would do the I/O. But if you have the node local SSD, you have kind of these 400 to 500 megabytes per second on each node. So the idea is that we include these node local storage into the HPC hierarchy, right? And we want to deploy a lightweight distributed file system on a per job basis that has a temporary lifetime, in which we stage in the input I'm sorry, I was just distracted by chat. That we have to stage in the input data to this distributed file system, and then later the output data back out, right? And also one of the things that we've seen is for the semantics that the HPC applications have, and we have some studies that are based on that some features are not actually used. Like for example, rename I know that we have now an application at Admire that uses rename, but we have seen that it's actually not used. So we only offer file system feature, which are actually required by most all applications. They started out much stricter than it actually was in the end. Yeah. And finally, of course, when you have these isolated file system, you don't have interference, right? And you improve the data locality as well, because you can decide basically what kind of data distribution you want in this file system. So what we want to do in summary is we want to go from this, where the data manipulation rely on the parallel file system, and where we have uncoordinated access based on random I/O or whatever, where the nodes actually work on the file system, on the parallel file system directly. We want to go to this, right? So we span a distributed file system over a number of nodes, and while the application is running, it will use this distributed file system so that these harmful I/O patterns like random I/O or a lot of metadata operations can be handled by that. And then later, we only stage out the output data in a more sequential fashion like the parallel file system is used to, back to the parallel file system, because the distributed file system is temporary. So in the end, the data that is in the nodes will be destroyed when the job ends, right? So this was the goal and the motivation. So now to GekkoFS and the core challenges. So the core challenges that need to be addressed are the following. So first of all, the most important one is obviously scalability, right? If we don't have scalability, there's no reason for the file system to be there. And initially, we focused mostly on the metadata performance because we saw this as the most important workload. But also we focused on random I/O and shared file I/O and things like that, right? So we wanted to have a linear scaling by the number of nodes. Like if you have twice the number of nodes, you have twice the amount of metadata throughput or I/O throughput. Then the next important point to us is the fast deployment, right? If you start a file system at the beginning of a job, it cannot take a couple of minutes because this in the end just wastes resources. And the question is then, of course, who's going to pay for that time if the job is not actually starting? It could either be the user within its job, or it could be just the normal job setup time. So it needs to be fast. And initially we said, okay, it should be less than a minute, and we'll see later on how much it actually is. The next part is the user space file system. There are a couple of reasons which I go later into, but it's of course for development, but also that you don't need admin support while using it within your job. And finally, hardware independence with regards to the storage and the network, right? It should work with the native network protocols that you have in your supercomputer clusters, which is, for example, InfiniBand or OmniPath. So first off, for the scalability part, the most important one, and it's generally usually a question of POSIX versus scalability. And there are a lot of papers out there and a lot of discussion that has gone on for years as what do we do with POSIX, because it obviously hurts scalability. And why is that? Because basically when you look at the POSIX dictated semantics, you're kind of forced in a corner in how you have to design your file system. And this is not only because of POSIX itself, but how file systems connect to the operating system, right? Usually, if you have a kernel-based file system like GekkoFS or Lustre is the case, it has to use data structures that are part of the virtual file system, which is kind of this abstract file system, so that every application has the same I/O interface in the end. Right? So we have these, for example, these directory blocks, which are basically used to see how many entries are in a directory. You have inodes, which represent basically the metadata of the file, like the size information, all the permissions, things like that. But these are not designed for parallel access. And what that means is if you modify them, what the file system have to do to not get in a corrupted state is to log these data structures. And once you start locking these data structures in a distributed setting, then what happens automatically is that you have a lot of locking communication. You have situations where, I don't know, for example, you do a standard ls minus l, right? That is usually a big problem and could take a while on a big directory. And if you have at the same time creating directories in that directory, you have actually a lot of lock revokes as well. So you have a lot of internode communication just for the distributed locking manager. This leads to high code complexity, and then this combined with kind of the file system protocol that the VFS dictates for you, you end up with a poor scalability. And we've seen this in common parallel file system, and it gets very obvious if you look at the code of these parallel file systems as well. So what do we want to do instead? Basically, we don't want to use these inodes and directory blocks that are a legacy data structure from when we basically only had one core in a single machine. So I want to get away from that. And then we also want to remove more metadata that we don't need in this temporary distributed file system setting. And for example, this can be time steps or permissions, and more on that later, but they can be optionally removed. Also, but most importantly, is that when a file system client does an IO operation, it should be able to send the request to a server without contacting any other central component, right? Not a metadata server that could become congested and so on. And then when the server receives this message, it will just handle that request independently. And we believe that this is vital to be able to have the scalability, that you have no central components. So another part is, I've talked about it before, we want to focus HPC applications, and we actually want to favor applications over user file system interaction. So when you're using a file system normally, like a Lustre or on your shell, on your machine, you're obviously doing change directory, you're moving files around, you're renaming them, and you're doing these operations that are not often used on HPC applications. Then we want to weaken up the consistency a bit. This is mostly for operations that we call indirect operations. So for anything that is a direct file operation, which is a create a specific file, write a specific file, or read a specific file, this is strongly consistent, and we can get away with that without any locking. But if you do an ls-l operation, then it gets very difficult to do this in a strongly consistent way, because we have no locking. We are not able to lock a whole directory while other people are inserting files into that. So if you have a strong POSIX requirement, you would reflect the state when you do an ls of what is currently on the server. And we cannot have that if we want to be scalable in that sense and no locking. Also, if we're not using inodes, we're just using path, and we can have a flat namespace. This means we don't really need directories anymore. Like, of course, you can still use them, but they're not represented in the same way as for normal file systems. So when we have a path, of course, you see, while looking at the path, what the directories are in that path. And further, we can simplify the file system protocol if we're not part of the VFS. And I've already talked about before, no locking, no central component. So this is for the scalability part. Then for the core design, we have, of course, the fast startup. And it turns out that for around 512 node, we can start the GekkoFS servers up in less than 10 seconds. Of course, it kind of depends on the state of the cluster and the network communication. And in this case, we're just using MPI for that. And this is possible to get such a fast startup because we have decoupled file components. In other file systems, you would have communication between the servers, and then the more servers you add, the longer it takes to start them up. The next part is the user space file system. Again, we don't want any admin support, because if you have a kernel file system, it gets more difficult to actually run these file systems on a cluster, and admins, rightfully so, often get concerned if you want to actually have a new kernel or a kernel module for that. And finally, hardware independence for storage and network. So I want to talk a little bit about this problem about how to get a user file system interface, because there are a couple of ways how you can create a file system. So the most common one is the kernel-based approach, which is the ext4 or the Lustre approach, right? Where it's actually positioned below the VFS, and you use the normal glibc, right? Your GNU C library to do your fwrite or your pwrite or whatever, and it will go to the VFS, and then in the end to a Lustre. The problem commonly with these kernel-based approaches is that they take quite a long time to develop, because you have to basically make sure that everything works properly to not, for example, get a kernel panic and to crash the node. But there are also latency concerns for future storage devices. Like if we look at non-volatile memory, there are works that have shown that the overhead of system calls is actually too much to get the full performance out of these IO devices. And since we also want to focus these devices and admire, it is also important to basically not use kernel-based. Kind of a compromise is the Fuse library. And the Fuse library is, it has a kernel module that is oftentimes available nowadays, but not on all clusters, to be fair. But it allows you to very easily create a user space file system, right? Like you can create just an easy custom file system. But again, you need some admin support. You cannot just use a Fuse file system if you don't have the kernel module or the rights to mount a file system, because a mounting operation is also a privileged operation. You cannot actually mount this. And also, we have seen in the past that there are scalability concerns as well, specifically for metadata operations, because again, it's dictated by the VFS because it's using the kernel module that is attached to the VFS again. So yeah, it's also something that we looked into, but we didn't want to do in the end. Finally, the last two are to use an IO library, which is here. So the application would use different IO operations that are not POSIX. So these are specific ones, but you would need to rewrite your application, and this is often not even possible with the application. So we didn't want to use an IO library. So in the end, we settled on the only kind of solution left, which is the preload library. It has its own set of issues, but what it basically does, it sits between the application and your user space file system. And in this case, user space file system is just another process, just another program that is running. And basically, we intercept IO calls that are coming from the application. The problem with raw preload, with preloading, is that if you intercept everything. You intercept everything from the libc, and basically in the end, to support something where all applications work with, you would have to re-implement the whole GNU C library. And given that it's updated all the time, this is not really a solution that will work in the long run. There's another solution, which is building on the LD preload approach, which is system call intercept. And this comes from Intel's persistent memory project, where you basically only intercept system calls. And you do this by basically rewriting the machine code, doing trampoline instruction in there, so that we only do the number of system calls that are not often changing. And of course, they change a little bit, but the high level GNU C library can be basically untouched from our side. So we're doing that. We're doing the preload library with system call intercept that you preload with the LD preload environment variable. So to summarize, what is GekkoFS not? It is not supposed to be a long-term general purpose file system like Lustre or GekkoFS is. To be able to have that, we would need a lot more features, and we also believe that it should be a strongly consistent POSIX file system, but it's just another use case for us. In the end, GekkoFS is ephemeral. Its lifetime is linked to the application and workflow, and therefore we have other kind of assumptions and things that we need within the file system. It is also not multi-user, and multi-user in that sense doesn't mean that it cannot be used by multiple users. It means that you're not able to use the normal permissions, right? If you have access to the file system, you have access to the whole file system. Multiple users can access it, but you don't have the same kind of user privileges. So if you're a normal user, you know what the file system are, you can use it. And again, GekkoFS cannot be really considered POSIX, although the IO operations are strongly consistent. We support most of the POSIX IO API, but we discard some of the semantics in favor of performance. We're also able to offer specialized APIs. So I've talked about the IO library. We can also do that. You can directly link to our application and then use it without LD preloading or without preloading the file system. So what GekkoFS is, and I want to emphasize this at the moment, is that it is a high-performance distributed file system, and it was supposed to be for a single application. And it allows you to aggregate the node local storage, both in capacity and, of course, performance. And then you have a shared namespace between all of these nodes. So basically combine all the SSDs. You have the performance of the SSDs aggregated, and you also have the capacity. Another very nice thing is that because it is supposed to be used by a single application, you can start configuring it in the way that you want to. right? You cannot do this with a normal parallel file system because it has to do the normal case. But what we can actually do is we can change how the file system behaves for an application. And this can mean the data distribution. This can mean the consistency model, something that is more suitable for your application. Of course, this is the intent to do this. And one of those will be obviously the malleability part in the Admire project. And the third part, it is easy to use because it runs in user space. Anyone can do it. You don't need to ask any administrator if you have access to the SSD. Without an administrative support, you can use it. You can also run it in your, I don't know, in your memory if you want to, right? If you have access to specific storage on the node, you can use the file system as well. And later I'll show you the numbers, but it is highly scalable. It scales linearly with regards to node count. And also the way we internally look at the access patterns, how we internally process the access patterns that we get. We also transform them. So basically, it doesn't matter if you do random or sequential I/O. At some point, and I say this with an asterisk because there are, of course, some caveats here, but if you are above the block size, or we call it chunk size in our file system, the below file system always sees sequential access. And it also doesn't matter if you use file process or shared file. For us, it's literally the same, internally at least. So then, and this is kind of the bridge to Admire. What will it be in Admire? It will support longer living workflows. And of course, we talked about this in the Admire meetings at length. It should support several applications that are basically, that could be running in consecutive order within several workflows. It could run for weeks at a time, so that once you stage in the data from, or the input data from the parallel file system to the GekkoFS file system, it basically amortizes better. But if you have a longer runtime, then of course you also need error correction mechanisms. What happens if a node crashes? So you don't want to lose this data that is currently in the file system. But this is something that we also want to do as part of work package 2 without losing the performance that we have. And this will be a big challenge, of course. Then the next big part is the malleability in Admire. And for now, what we mean by that is that we can increase or decrease the number of file system nodes, which of course affects scalability and the performance that we have. And this should be while the system is running. This will involve some moving around of data, of course, but this will be part of it. Then also we can control quality of service. So if the intelligent controller in Admire tells us, well, you need to reduce the bandwidth for a bit, or the CPU consumption, for instance, we are aiming to do that also via the API that we have in Admire. And then finally, also parts that can be malleable is change the caching aggressiveness, where you could have a very good write cache in the beginning of an application, and later you have a better read cache, right? This you could also do depending on the application that you have. But this is something that we still need to add to GekkoFS. Then also we will support fast storage technologies, like persistent memory, non-volatile memory, in a native way with the proper interfaces here. And then, of course, integrated into the Admire ecosystem. This is specifically the IO scheduler, and the IO scheduler is basically controlling the ad hoc file system like GekkoFS and Admire. It will start up and shut down the file system, but it will also stage in data, right? And finally, we have the connection to the intelligent controller to tell it if we change a configuration of the file system, we let the intelligent controller know. And then we have a connection to the monitoring module in Admire, so we let them know what is the current load in the file system, what is the bandwidth that we have in the last 5 or 15 minutes, something like that. So, and just to give you a picture with the all so familiar image in the Admire architecture, which is here, the ad hoc storage systems. There are more ad hoc storage systems in Admire. It's not just GekkoFS, but GekkoFS is placed here. And again, it's connected mostly to the IO scheduler, but then also to the work package 5 sensing and profiling. There will also be a hierarchical storage management data flow between the backend storage, whereby GekkoFS will work as a Lustre extension here. And this is done discussion to how this will be done. So now that we know how it works, how does the architecture look like? And I said again, it is lightweight somewhat. So we have two components again, which is the server and the client. The server we call a daemon. And basically what the server does, or the daemon does, is it has a RPC server components to process incoming requests. It also has an IPC component because if the client is on the same node, we don't need to do RPC, we just do it by our shared memory. Then we use a RocksDB key value store to store the metadata and our namespace basically. And then of course we are connected to the node local storage. RocksDB is also running on a node local storage, of course, but the node local storage is mostly used for the data, right? And we transform the data that you get from the applications into so-called chunks, which are just parts of the buffer that are distributed, right? Then we have the GekkoFS client, which is only a library that you preload with the LD preload environment variable. Again, in the demo letter, you see how all of that works, but it's also very simple. You have the system call intercept component that allows us to just intercept the system calls. So therefore, the GekkoFS client is placed logically between glibc and the application. Then we, of course, we have the RPC clients, to talk to the other daemons. And that is basically it. We have also a file map here, which basically takes care of the file descriptors, which are normally in the kernel, but since we're not in the kernel, we have to re-implement a little bit here. Because as you know, a lot of IO calls are not all IO calls are working with path. You have also some, if you do an open, you get a file descriptor. And then if you do a write later, you use this file descriptor, right? So we need to know what this file descriptor corresponds to. And this is basically it, right? We do these, we do the communication via RPCs and data movement via RDMA. If we have OmniPath and InfiniBand, we can do this with the Mercury RPC framework, which we use for that. And we finally, of course, we have the parallel file system, which the long-term data resides in, which is staged in or staged out correspondingly. So how do we actually achieve the data scalability? Here's just an example of one of the data distribution that we have. The file system is built in a modular way, so we also add a number of another data distribution within that mire. The ones that we have started with is the white striping approach, and white striping basically just means that you are spreading the data over all nodes that are available. And this might be familiar in Lustran, where it's called striping, where you could stripe all the data over all object storage targets or OSTs in Lustran. So how does that work? We have the application, which issues a write, for example, here on the left side. We intercept it, then we have the write buffer, and then we just chunk it, right? So these are just boundaries, and by default, we have 0.5 megabytes of chunks. And then via hashing and the node number, we compute the destination, and all chunks that are going to the same destination will be packaged, right? This is happening here. And then these packages based corresponding of possibly multiple chunks are just sent in parallel to the daemons that are for the specific package. This is happening in parallel. So all these chunks are happening in parallel. And then in the end, these chunks are just saved on the local file system. And if you would have access, or if you would look on the server's side, you can actually just read the chunks, right? It's not a specific, kind of a make file system kind of way. We're just placing these chunks as a normal file system file on the node local file system, and that's it, right? So you can easily actually just look into that if you would choose to do so. But of course, you don't have to. If you do a read, it happens in reverse, of course. Again, you would chunk the read buffer up. You know where kind of the read buffer should go to, and then the daemon just fills that and returns it again via RDMA. So I showed you before the performance variability that you have, where you have different performances based on the time of day and the day of the week. This is again the same picture. We have Mara 4 here again. And the blue dots here are now GekkoFS. And of course, because you have no interference really anymore, and because it's just a single application using them for the specific IO workload, you always get the same performance. So that means as If you know the number of nodes, if you know the storage and the network, we basically can tell you what performance you're going to get. So now to the evaluation. To just give you a little bit of an idea of our performance. We have two test systems. One is Moron 2 supercomputer in the University of Mainz. We are using, in the sake of these numbers, we're using two micro benchmarks, which is the metadata and d-test benchmark, in which we create 100,000 files per node. And then we have IOR, which is a data micro benchmark where you can replicate a lot of access patterns, specifically those that are challenging for parallel files. Right, you can create a workload that actually doesn't work well at all for Lustre, for example. In our case, we have a SATA SSD on each node. It has kind of the same performance that you've seen earlier, which are 400 to 500 megabytes read and write performance per node, and all operated also synchronous because we have no caching in GekkoFS. We will, in Admire, we will add caching to GekkoFS, but for now we don't have that. And of course, this makes it very easy, of course, to have a strongly consistent I/O system. So for metadata performance, first of all, I want to show you the kind of performance that you put it against Lustre in our system. Of course, these are two entirely different use cases, and comparing them only should give you an idea about the performance that you can gain on our specific system. Of course, in another system, it might look a little bit different, but case in point, what you can see here, if you increase the number of nodes, you basically have the same performance, and it saturates very quickly at 4 nodes here, right? You can't get any farther than that. For GekkoFS, you have linear scaling with a number of nodes. I also want to talk here a little bit about the unique tier and single tier kind of performance. And usually, what you have on these I/O systems is that application or people who develop applications are usually asked to create the files so that the process is using its own directory. So that, and this is basically coming back to the whole locking problem. If you have multiple processes operating on the same directory, you get locking issues, and then you basically get lower performance. You see this here specifically in the beginning when you would run all of these all of these processes in a single directory. You get much lower performance as you would do it in a directory per process, right? But in the end, the more nodes you get, at some point it just saturates. So to get a little bit of more fair comparison, we have GekkoFS compared with BGFS. BGFS has a beyond, also a beyond part, and the beyond part is basically be able to replicate exactly the way that we are doing. We're starting the same amount of metadata nodes and I/O nodes as we do with GekkoFS on the number of servers, so that we also see linear scaling if you do a directory per process for BGFS, which is the yellow one here. Okay, GekkoFS still is a lot faster, basically the same performance that you showed before, but it's here much more apparent if you only operate in a single directory, how little performance you get, metadata performance in this case, compared to if the process would use their own directories, right? For step performance, the performance is somewhat similar, but again, for single tier performance, it reduced a little bit. So for I/O performance, there are two things I want to show, and I don't want to now bore you with always the same picture. If you do random I/O and shared I/O, it looks basically always the same. It's linear scaling, but what we have here is these 4 gigabytes per process that we're writing to the SSD. And these blocks that you see here are basically the I/O request sizes, right? If you do a write and you don't need to do 8 kilobytes at a time or 64 megabytes at a time. And of course, the smaller you go with your I/O request size, the latency kind of takes over. Compared with larger I/O request sizes, you see more of the bandwidth available. And what we wanted to look here is that we aggregate the local SSD performance together, which is kind of the white roof on each bar here. This is the potential that the SSDs would give you if you would run them locally and aggregate the performance, which is just adding up, right? Because you don't have a distributed file system on these SSDs. And the performance that we see here on GekkoFS is basically the efficiency, how we use the SSDs. And also it will show you kind of the network cost in the end, right? Then we also can compare this again with BGFS, and the performance here is very similar. You could kind of see a trend where BGFS is a little bit better with smaller request sizes than we are. This might be of caching because we don't have anything, so we are very vulnerable to latency prone operations, but we are something a little bit better in the bigger kind of operation because we can then in parallel move IO around in the system. But for the most part, it's somewhat different in this workload. So somewhat the same in this workload. So the next part is the IO500, which is the next gen IO cluster prototype, which are a number of nodes, but most importantly, each node here has these 2 Intel Optane persistent memory modules. And we use these in these IO500 tests. Each node also has 2 OmniPass network devices that we can use as well. And yeah, we use this for our IO500 submission, but also for Modern 2, but in this case, the IO500 was better. So if we look at the results that we had in SC 2020, of course, this kind of IO500 got more popular in the past years. So the bigger systems with more hardware capabilities that we had would also submit their results. What we'll show you here is the 10 node challenge, and that basically means that you can only use 10 client nodes, which is helpful for us based on the hardware side, but you can still use however many servers that you want. And basically what IO500 does is it has just a whole bunch of different kind of access patterns that you would see in applications. There's of course random IO, difficult small random IO, but you also have big ls-l operations that are also included in the store that you see here at the end. So we are in 2020, we were still on top 10, but I wanted to include the slide specifically because there was a new contender in this specific year, which is called MadFS, and MadFS is actually based on the design of GekkoFS, and it is developed in the Pengcheng laboratory by MadLabs in China. And they're running this on their very powerful Atlas 900 system, where they have a lot more hardware available than we have. But it's not based in GekkoFS in the sense that they use the same code. They have kind of the same design. They use the same kind of hashing algorithm, how we distribute data. They're using the same RocksDB. They're using also system call intercept, but I couldn't do kind of the same GekkoFS hardware because at that point there were some problems with ARM, which we no longer have. So GekkoFS is also now working with other architectures like PowerPC or ARM64. But this kind of shows that the design that we are having in GekkoFS is very much able to scale well, even on very fast systems. So there are other success stories that I just want to showcase here. Before I start, maybe from one Admire application from NEC 5000s, we did some very preliminary evaluation here, where we've seen that we already get, just by using it, a 20% increase in IO in runtime for NEC 5000. But of course, we will have to look more into that, and I'm optimistic we can get a lot more out of that. But yeah, we have here a couple of applications like check on restart workloads, which are of course very important for a lot of applications, but we get a lot more bandwidth out of that with GekkoFS. So lastly, before we go to the demo, I just want to quickly talk about distributed deep learning with GekkoFS because it's also relevant for Admire because there are 2 applications which are in the deep learning domain. And this was a publication last year, again on the IEEE cluster, where we did experiments with the ImageNet set and TensorFlow. And what we basically seen that you can easily just use it with TensorFlow and then it works. But we looked specifically into kind of how fast it is compared to what deep learning applications usually do if their data set is small enough. So if you have a small enough data set, so this is like here the step time for every step, lower is better in this case. And we have different kind of workloads here. REST 50 in this case is clearly CPU bound because it doesn't matter if you use the parallel file system or the local memory. So if you have the same performance here, that means it's IO bound. But for this REST 18, for example, you see it's much more IO bound. And what you basically see is that the performance, of course, you get a little bit of overhead for GekkoFS if you have it on the same node. But as soon as you use distributed learning with 8 nodes, yeah, then you also are very near to the local step type. But you cannot, of course, do this if you only have your local nodes available. So this is specifically relevant if you have a work set which is much bigger than what you can place on a node. So what you would usually do in a deep learning application is then you would create so-called shards, which are basically sets of the work set, like a smaller subset of the work set, but you have to be careful when you use them because you won't introduce any biases, right? For GekkoFS, this is an issue. You just have this big shared namespace and you can just move in the whole data set and every node has it available. So you don't actually need shards anymore if you use this. The second part that we want to include here is the staging, because of course you need to move in the data to use it. And again, if you're looking at the combined staging here, and for the local cases, this means that we actually split the data into shards so that every node gets its own subset, which is the usually done way. But for GekkoFS, we only have to do it once. So we need to use the whole set, move it into the GekkoFS namespace. So the 64 nodes have the full data set available, and actually the time it takes to move that data into the 64 nodes is of course the same performance than if you would do it locally but without shards. So then we have just some that is also used in deep learning as a reader operation, which is done ls minus l. And in this case, this is the full data set ImageNet. And if we have 64 nodes, we are also very fast on this ls operations, right? It takes 2 seconds compared if you have this on a local XFS, for example, on an SSD, where it takes close to 20 seconds. So now before the demo, what are our immediate next steps for Admire, not for a whole project, but the immediate next steps in the next couple of months? Of course, this is continuing the integration to Admire, which will, of course, be part of the whole Admire project duration, but is, of course, first of all, connected to the IO scheduler. We're already having some statistics available that will export to Work Package 5 via the Prometheus exporter. Then also what we want to add is management tools that makes it easier for you as a user to start up, because at the moment you have to rely on SRun. It's not very difficult, as you will see later when Ramon is showing you that, but we want to make it even easier. Further, additional software support. At the moment, you need to kind of compile your own dependencies, and this is some of which can cause issues. I will show you that in the next couple of minutes how these compilation works, so they can already try it. We already have comprehensible scripts for that, so that you can easily use it. But there might still be some issues based on the, cluster and environment that you're using. So what we aim to do is also to integrate GekkoFS into this SPAC application. And SPAC is basically a package manager for user space, right? So you will basically install stuff, applications from the SPAC repository into a user pass on your cluster and your space on the Lustre, for example. Then at the moment, we only support POSIX.io. This is syscall intercept. Of course, we will also do the steps now to support MPIO, which of course is important for HPC applications. And we will do this via the Romeo layer. This is also how Lustre is doing that, for example. So we will do this as well. And then finally, add rename, which we can do. But of course, there's a trade-off since we only work with path. So we need to be careful how we are doing that. But yeah, this is something that we will work in the immediate future here. So I would then directly go to the usage and demo, perhaps. So I will now make this a little bit smaller. I hope you can still read it. Maybe I can make it a little bit bigger for you. That's not what I wanted. So I just go with you over that, how you actually use it. So first of all, we have in our Git repository, we have just released the latest version 0.9.0, which is the latest stable one. But you can also, just clone the master branch. But this is more, of course, more recent. There may be bugs into this. There may be bugs in this master branch. But usually it should be mostly stable. So what you do is you clone, include the submodules because we're using the submodules on our GekkoFS repository. Then again, because we're relying on Mercury and RocksDB and other dependencies, which are kind of difficult to get and they're not available on the cluster environment, so you have to download and compile them yourselves. So that you don't have to do that manually, we have the scripts available for you, which is the download dep, compile dep. The download dep is basically just compiling them. It's just downloading them to a specific directory that you define. Right, this is just if you would download a bunch of Git repositories, and then the compile script would just compile the sources that you have downloaded here. Right, I usually call it Git, and then you will put it into the install folder. The important part is that because you have kind of a different path in your user now that you rely on for your libraries, you need to also add this install lib path to your LD library path for the system, right? So that you can actually find these libraries that I use for GekkoFS. So I will actually start this now because it takes like 5 minutes to compile them before I talk to you about the rest. So I hope you can see this. And please let me know if you don't see my shell, okay? So you just scream, just yell if it doesn't work. So I will just first clone the Git repository here. Of course, it's not downloading all the submodules from our project and from the project that we're including. So that's it. And then you have your GekkoFS available here. I also have a large file here in this specific directory, but there are some other, I just want to show you this now. So when you download these libraries, these are in GekkoFS scripts, and then download dep, as I showed you. We of course have a help page here. And what you can see here is that we have something that is called profiles, right? Because depending on the system you're using, kind of the profiles can change. The default profile is the one that you use if you don't say anything, if you just put say the password where you want to store your dependencies. So at the moment, if you do -L, you list all the kind of profiles that we have for the different versions. Of course, you have the latest version, which is 0.90, and we have these kind of dependencies. We have these kind of profiles that you can use. So for example, if you have a new cluster and we have very delicate version dependencies here, we can just add them here, and then you have a specific profile for that. But usually we have some generic ones for InfiniBand or for OmniPass, which should work right off the box. So you can look into the specific profiles and see what kind of versions and what kind of dependencies they have. So again, you go into GekkoFS and scripts, latest, and then let's look into the default one. So, and these are kind of the dependencies that we have, right? The for capstone and so on. And these will be compiled now. So next we compile them, which I showed you on the slide how that works. I'll just paste that here. Right, compile, say where the downloaded dependencies are, and where to install them. I already set the LD library path. Maybe let's just quickly show that to you. So the LD library path is here, which is GekkoFS depth, install lib, and GekkoFS install lib64. These are the ones where it will be installed to. So let's compile them. Oh, I didn't download it, sorry. All right. So let's download it first. Like that. So we're now downloading all the dependencies with the dldep scripts. And now we compile them. And there we go. So we let this run now for a second. We'll take a few minutes and then I finish the slides. So I hope it now switched again to the slides. So after you have compiled your dependencies at the specific path, you then build GekkoFS. And this is just CMake. What is happening here is that you have a CMake prefix path, and this prefix path is basically used that we tell GekkoFS where the dependencies are that you just compiled, right? And then also if you want to install them somewhere else, then in the build directory, just put them into your own path that you want, and then it will be installed if you run make install. But then what you will do just make install, and that's it. So next, you will have, so the two things that are happening then is that you have a binary available, which is the GekkoFS daemon, which is just a normal application that you can run. And you have the interception library, which is not an executable, which is used by LD preload, right? Again, between the application and syscall, and which is between system call and the application. So when you start a service, you would just do this on all the nodes that you want to start the file system on. So first off, what you do is -r is basically telling you the root tier, and the root tier is the data path where you want this GekkoFS data to reside while it's running. And this, of course, could be the node local SSD. It could be an in-memory file system or a RAM disk, right? Whatever you want, basically, as long as it has a path and you have access to it, you can use it. And then next we have a -m, which is the mount directory. And for the mount path, I want to emphasize we are not a kernel file system, so you don't, like, it's not the same as if you would call mount and then mount an ext4 and XFS that you might have done before. So if you type mount, it will not show up as a mount point. It is, so in that sense, it's somewhat a pseudo mount point, right? We will pass this to the daemon so that basically the clients that connect to it know what path they need to intercept, right? So everything below the mount path was part of GekkoFS. And then finally, how do the clients know which kind of servers are part of that specific file system instance? If you have 4 nodes, for instance, right? You would start this command on the 4 nodes, and you can do this with srun, right? Which Ramon showed you later. The daemons will also register themselves. And for that, you have to use a so-called host file. So by default, it's placed into the same directory. I'll show you how that works in demo. But you do -h, and then you use a path on a parallel file system. So it's used in conjunction with the parallel file system. All the GekkoFS daemons will then write into that same host file on your Lustre, for example, on the same path. And then you have 4 lines in there. Each line corresponds for a daemon, and then you have the address in there, how the clients connect. So you let the clients know about this specific host file path by using a environment variable. Again, we have a library. We cannot really pass anything outside of just environment variables. So we're using this, and this here is the same host file, the same path. So then choose a client finally. So just a normal, simple operation. You use the cp command on your shell, and then you can copy some input data from your home directory, for example, and then you place it below the GekkoFS mount path. And this is then some input data also in there. So if you would do this without LD preload, what would happen is that you copy this input data to whatever path you're using, right? You're not using GekkoFS, so it's not in GekkoFS if you don't use LD preload, right? So you have to always make sure to use LD preload and to set it if you want to use it. So if you have an application, API application, you can just also pass LD preload as an environment variable. So once you do that, you set LD preload, you do your copy. So our client library will then intercept this operation, which is first of all a read operation to this input data in your home directory. This is not below the GekkoFS mount path, so we just forward it to the kernel, right? Which will then read the data appropriately, and then for write, it is within the GekkoFS path. So this we then intercept and forward to our daemons. So this is how it works, like I showed you this before. So this is generally how it works. I now show you everything on the shell from now on. So now it's also finished. That's great. So I can scroll a little bit up. So you see here that RocksDB has been compiled. Scroll a little bit more up. You can also see that Margo and Mercury and Argobots, all of these RPC stuff that we need is also compiled. And it has been installed to that specific directory. So if I would look to this GekkoFS deps directory in install, right, where I compiled the dependencies to, you would see I now have bin include lib. This is the normal hierarchy that you see if you compile something and install it somewhere. And then if you look in lib, you see Mercury, you see RocksDB, and so on, right? So now we can compile GekkoFS. So just check my notes. Okay, before I do that, I just want to refer to our README. To our README, and you can also refer to that. And here you can also see a step-by-step installation guide. You see what kind of dependencies you need beyond that for Ubuntu or for Debian or CentOS or something. These are like normal dependencies that you usually need anyway, so they're most likely already installed. But if you want to actually test GekkoFS and want to use our testing framework, you need Python 3 as well. And basically the PyTest kind of framework. So there's more information on here. How to run GekkoFS, which is basically the same that I just showed you on the slide, just a little bit more detail, how you actually use it. I go a little bit further down. But also more importantly, you have a section here which is called logging. So we also have a quarter logging facility. You can log the client library by passing the libGekkoFS log environment variable. Here are your options that you can use and what they produce. And of course, you can also log the daemon side because they're two separate kind of things. And you do this like this, GekkoFS log level. Okay, so now let's compile GekkoFS. We go into GekkoFS and we make a build directory. And then we go into that build directory and then we run CMake. So I do this now like this. Again, we compile it, of course, in release. We do the prefix path where the dependencies located that we just compiled. Where we want to install them, I just want to install them to .local, which is just the kind of normal user installation kind of path. But I also want to build tests, which is not default. So the CMake will now take a little bit longer because we need to download a little bit of testing frameworks. So yeah, just bear that in mind. So this is now the CMake running. I scroll a little bit up. So what you can see here now is that, for example, RocksDB, it has found the dependencies that we just compiled, right? It is in GekkoFS steps, install libRocksDB. So, and now we can compile it and install it. And again, this now takes a little bit longer because of the additional testing stuff that we need to compile as well. Just run for a second. So also what you can do is just minimize it here for a second and go to another window. You don't have to write LD preload and then the library, which will be placed here every time. I would recommend to do this on a cluster when you use NPR, but if you just test it around, what you can also do is you can define an alias, right? So you can do an alias and say, okay, I want the GekkoFS command actually to do this. Right, I already done this. So if I look at GekkoFS, this is the alias to LD preload. So what I can do is GekkoFS and then copy, and then I have already it preloaded. So this is just a little bit of a tip that you can do. So it is now almost finished. That should be it. Perfect. We have installed them here into my local directory, bin, GekkoFS, and lib64 is our intercept library. So and if you want to run the test, you can now just make test and it will run the test. This will take a couple of minutes, so I will go to another kind of screen again to show you how GekkoFS works. We go to the top right here. So again, I have my GekkoFS daemon. I have this GekkoFS daemon in my path where I just installed to. This is why I can just use it like so. You can also, of course, use it directly in the build directory. And of course, we have a help page here. Make it a little bit bigger. So again, you have the -m, the -r, the mountie, and the root tier. But what you can also do is, and this is specifically more important for the clusters, is that you have different kind of network interfaces, right? You perhaps have a management network, which is slower, and you also have the InfiniBand network. So you would use just -l to say the daemon, please listen on that network device, and not on, I don't know, a local device. So yeah, we're going to do that now. We also define the host file. So let's do that now. So we start the GekkoFS daemon, and we'll just do this in memory now. So the root tier will be in temp, GekkoFS root tier, and the mount tier will also be there. And we will listen on the Eno1 network device. And in my case, if we look at the network device available, of course, there's the local host one, which is right this one, 127, of course. And the Eno1 is just my normal Ethernet, so we'll use this. So someone else in the university could now actually connect to it if I start. If I would open the ports on that, of course. So, and I also, of course, want to say I want to create the host file, and this is placed in the home directory GekkoFS host file. So I start this. It is now running. It will not close. Of course, you can start in the background, and you have to shut it down manually. Of course, again, we have this management tools later, which will help you with that. So the paths are now also done here on the bottom left. This is how it looks like. It's all passed. And we have a testing folder in there where you can actually see if there's any error on what it is. But there were constraints of time. I want to skip this now. So now we have the daemon started. I will just show you now how the host file looks like. So I go into the home directory and then GekkoFS host file, which is up here on the top left. We have the host name, and then we have the protocol, which in this case is sockets or TCP, and then the IP, which it is listening on. Okay, this is what the client uses. So we have talked about this. We need to define this GekkoFS host files for the clients, and we do this here on the bottom left. I go on the workday again. So define this with export so that it's just there as an environment variable. Okay, and now it should work. So if I would now do an ls on this mount, in this GekkoFS mount here where I just started at, it is empty. So if I were to move this large file that I have here to this mount here without GekkoFS, I would just copy it into the temp directory, right? If I have an ls on it, there's no GekkoFS involved here. So when I do the same thing, if I use GekkoFS and look into this mount point, it is now empty because now I'm actually using GekkoFS. Okay. So again, I want to emphasize it's kind of a pseudo mount point, and it's a little bit different than what you used to perhaps. So, but I also can just copy that large file to it into the mount tier, just like that, and it's already finished. And now I do an ls on the GekkoFS mount here, and now the large file is available. Notice that it's 1970 where it's created because we don't have creation time. So it will just use the default, right? This is one of the things that I told you. We don't store metadata if it's not used, if it's not actually required. So of course you can then do an, I don't know, MD5, for example, on both files, just see that it's actually the same, which of course it should be. Sorry, of course I need to specify the large file here. So in this case, this is then a read operation on the GekkoFS file. And there you go. So yeah, so this is basically how it works, right? Oh yeah, but perhaps I could show you just here on the, sorry. Going in the bottom right, if you go into the root tier that you defined, you can look in there and you then see what's going on. So you have the RocksDB, of course, in here. You have the chunks. The chunks are the data, and you see here, for example, the large file. And then the large file, you have all these chunks, right, which is the data. Again, 0.5 megabyte chunk size. So this is the 982 chunk. So not really magic here. So finally, before Roman will take over, I want to just quickly talk about something. When you have a star operation, right, something like, I don't know, remove GekkoFS mount dir. So now there is no bash completion here because bash completion is before it's intercepted. So even though you now get a large file, this is from that is the large file from the GekkoFS. But this also means if I do a star operation, which would just normally remove everything in the directory, this won't work, right? It will still be, the file will still be in GekkoFS or not. So apparently it worked. So I need to investigate that because it used to not work. But anyway, for MPI, just finally, if you would use MPI, see that it works. MPI minus 4 hostname, we have now 4 outputs. So you would use LD preload like this. You pass via -x an environment variable LD preload. I define it within here as well. And now we'll do this 4 times this ls, right? There's nothing in there. So yeah, that's it. And you shut them down just by Control Z or just sending stickint with the kill command, and then it will shut down. All right, then, yeah, this is it from my part, and I will now pass to Roman.
Thanks, Mark. I will share my screen also. Hope it works. Okay. So, yeah, I think you can see my screen. So I will do nearly the same as Mark has been done, okay, but in Minostrum. So I will skip some parts, okay, like the compilation of the dependencies, but it will be nearly the same. So first we will do the module load, that is the system that uses Minostrum for load the software that we need for compilation and running GekkoFS. So the minimal is Python, GCC, and CMake. Okay. Okay. And the next step is the one that Mark has been done, that is to compile the dependencies. Okay. That I will skip, but we have also, we have also a script that downloads and compiles at once the dependencies. In this case, it will be this command. Okay, this is the path where we download the dependencies, and this is the one where we install the dependencies. Okay, this is a 4-minute compilation, so I will skip that. And then we need also to build GekkoFS. Okay. For my instance, for example, I have a bash script that does it. We have some extra CMake options that you might find on the README. In this case, okay. We have also some paths, the module of if we forget it. Okay, the build path as Mark has been done. It's not really the same. Okay, but we define a release build type. We don't build the test. We don't install the test. Okay, we have some parameters disabled for increase the performance. Okay, and finally we have this CMake, this make install for Minor. We can run it. It's already compiled, but so I think it's really fast. Okay, this is the release version, and we basically install the two components. That is the daemon and the intercept library for the client. Okay. For Minor we have this model system, so we can set up GekkoFS in order to load all the parameters that we need, all the environment variables that we need to be more easy for the user to run it. So in this case, I can do just a use and a load of GekkoFS Java that I will show now what it contains. GekkoFS Java is the version that we use because we are testing some things. Okay, in this case we have the base, that is where we install GekkoFS. We have the daemon defined. We have the preload, okay, and we have the libraries. Then basically we set up the environment with the daemon, with the preload library. We define a basic log level, and we set up the path, okay, and the LD library paths. Okay. Only with this, we have all that we need to run GekkoFS in Minor. Okay. So how we run GekkoFS inside a Slurm, okay, to run some computing, some HPC software. In this case, we will run 5000. Okay, some example. It's a benchmark that contains MD test and IOR. Okay, we will run only MD test. So we have a sample Slurm file. Okay. So basically, we are asking for 4 nodes. Okay. We load all the models that we need for Minor. The basic ones. We load the GekkoFS module. Then we have this temporal path that points automatically to the SSD directory for the user in each node. Okay. And what we do is to define the GekkoFS mount point. Okay. And the GekkoFS root mount point. Okay. All inside in the SSD path on each node. Then we put the GekkoFS host file, as Mark has explained it before. That this is a file that should be visible for all the nodes, for all the clients. Okay, so we put them on the home directory of the user. Okay. Then we define some logs. Okay, this is not needed. It's only for the back. Okay, and at the end we define a command that executes the daemon, okay, with the mount dir that we specified, with the root dir we specified. And in this case, in -4, we need to define that we want to run the servers, or we want to listen the servers to the infinite band 0 device. Okay, this is to increase the performance of the network. Okay, this is the Slurp and Slurp job configuration file. Okay, so what we do at the beginning of the job is to run, okay, this command in order to delete all the temporal paths on each node. Okay, this is not needed. Okay, but we clean the system just in case the previous execution hang, or we have some leftover files inside the nodes. Then the next step is to execute one server per node. Okay, exporting all the environment variables. So we launch another is run. Okay, we export all the environment variables, and we run one task per CPU. Okay, this basically runs the command that we defined before, okay, to execute the daemon. Okay, and we run it in background. Okay, to do that, we need the oversubscribe command in order to be able to run more tasks than the specified in the configuration. Okay, this launches the servers. In this case, 4 servers. Okay, 1 per node, and we sleep 10 seconds in order to wait enough time in order to get it up. Okay, actually it's very fast, so 1 second or no wait will be enough, but let's keep on the safe side. Okay, what we will show is there are 3 commands. First, we will run a df. Okay, this df will be preloaded. Okay, with the library, so it will run inside GekkoFS. Okay, what we will see here is that the space that show up with this command is the space of 1 SSD multiplied per 4 nodes. Okay, we will run the same command without the LD preload, this one, and in this case we will see that only the space of 1 SSD is shown. And finally we will run this HPC test, this MD test, okay, running in 4 nodes with 120 processes, LD preload, okay, that will we write to the GekkoFS mount point, that is virtual mount point, and we'll create some files, okay? At the end of the job, what we'll do is to destroy the GekkoFS daemon, okay? We send Control C to all the servers so they can be closed in a healthy way, okay? Finally, we delete all the files that we have created, okay? So let me run the script. Okay, I send to the debug queue in order to. I hope it will be executed fast. Okay. Actually, it's running, and we can see the output. Sorry. Okay, let me go back. We have all the 4 daemons running, okay, on each node. We executed the df command inside GekkoFS, so we have nearly 900 gigabytes. Okay, this is the mount point, the virtual mount point. We run the same df without GekkoFS, so in this case, this is one SSD on one node only, okay, 200 gigabytes. We have also a file system here, okay, that is dep SDI. We don't have it on with GekkoFS. And then we launch the MD test. Okay, the MD test is running on the SSDs in parallel. Okay, this is not correct. Okay, but it's running on because they use another system call in order to get this information. But this is running on parallel, and it has created this number of files with 120 tasks in the 4 nodes. Okay. At the end, we destroy the daemons. All the job has finished. Okay, and it is the result. So you have seen here, it's very easy to run a command inside GekkoFS, okay, with the Slurm also. The only step that we need is to pre-run the daemon, okay, that this will be done automatically in Admire, okay, that you don't need to set up this one, okay, and then the command to run it is very simple, okay. Actually, it's the same that you will be doing without GekkoFS. You only need to specify that you are preloading the client. Okay. So this is all that I have for milestone 4. Okay. The only important points are these oversubscribed because we are running an S-run and we are putting the task in background. Okay, so if we don't use this oversubscribe, then we couldn't run this MD test. And the other thing is that we need to specify the mount point, and we need to preload the library. Okay.
Okay, thanks, Ramon.
Thanks, Mark.
So I think that's it. We're done.
Okay, thank you for the presentation. I think it's been very interesting. So now it's time for questions. I don't know if there are some questions. Let me see the chat. I see that there are some discussion already going in the chat between Mark and Assem. So I have one question related to the deployment. I mean, when you are deploying the system with SLAM, you deploy the, it's not clear if you are deploying the file system at the same time that the application, or are deploying the file system before the application.
We are deploying the file system before the application. We are using the same job description file, okay? So what we do first is to launch all the servers, okay? And
but you use the same script for
yes,
SLAM.
yes, the same script.
Okay.
It could be done in another job step, probably.
Yeah, that's my question. Why you could use job steps? Because how are you? I mean, if you want to have data locality, how are you sure that the system is getting the same nodes, or you are not sure? I mean, SLAM is deploying the servers in different nodes and the application in another nodes. Is that the situation right now or not?
Well, in this case, in this example, we are launching as servers as nodes we have for server. Okay, so we get 4 nodes and we launch 4 servers, and we launch 4 clients also. Okay, so we use all of them. If not,
so you are forcing you get the nodes, you are forcing the location of the servers.
Yeah.
And the client in the same nodes. Okay, thanks.
Yeah, but for example, we could have more servers than clients.
Mm-hmm.
Well, it's basically playing a bit with the configuration, with the job configuration file. Okay. The only thing that we need is that the clients see the host file of GekkoFS.
Okay. Okay.
Mm-hmm. For example, in NextGen.io, we have 2 sockets and 2 SSDs. And what we have done in order to increase the performance is to launch 2 servers per node. Okay. They have different IPs, and the performance basically doubles. Okay.
So they are sharing memory, I understand.
Yeah.
Okay. Mm-hmm. Okay. And the impact for the communication is all of them is made with Mercury, or you have other connectors?
All is done with Mercury. Yes.
Mercury. Okay. Okay. Okay, thank you. I don't know if someone else has more questions.
I see that Hamad raised his hand. And,
No. Hamad?
Hamad, can you speak? I am muted you.
Yes, thank you. I can't unmute myself.
Yeah.
Yes, I have a short question. I was asking myself if you use some kind of asynchronous I/O in GekkoFS. I mean, you can do this flushing of the buffer or the writing, basically with asynchronous I/O, or do you don't support that?
No, not yet. It is kind of on a roadmap, and we want to discuss this and how we can introduce it. But at the moment, everything is synchronous. So what it means is when you do a write operation on your application, then while your call is running, it will send that to the daemon will write it to the node local file system, and when this is done, it will respond to you.
Okay, but I can still, if I want to actually realize the flushing asynchronously.
But it
Asynchronous,
wouldn't do anything.
asynchronous to the application, I mean, of course.
I mean, yes, if you can, of course, do asynchronous I/O if you want to in the application, but it's not but we are not inside doing it asynchronously, right?
Okay, thank you.
Okay, I have one more question. This is Stefan Solberg. Since in the previous example, you started the GekkoFS daemon on the same nodes as running the job. So with many HPC systems, when you schedule a job, you have to explicitly specify how many hardware threads you are requiring. So if you're running the job and the daemon on the same node, how many hardware threads do I have to reserve for the daemon? Does it run on one thread, or does it have multiple threads?
Okay, so there are two things. First of all, you don't have to run them on the same nodes, right? It can be any kind of subset or overlap. It can be completely distinct set of nodes. But if you run them on the same nodes, there is some CPU overhead, of course. We need a number of cores. We're currently in the process of evaluating kind of how many we need. I would say probably like 2 and 3 realistically. But yes, we aim to reduce this. Of course, you can force via SLAM that GekkoFS is only using 1 core, but then your performance goes down. This is kind of the trade-off that you have to make. But yeah, one part of Admire is also to decrease the footprint and understand what is actually interfering with an application. And what we've seen in the past actually is that network interference is probably the most important for us. But there are things like priorities in networks that you can do. But yeah, I cannot say more about that for now, at least.
Can I specify when I start the daemon how many threads it will take?
To an extent, yes. We have kind of 2 components that need threads. One is RocksDB. We currently don't have support to specify it there, but we will add it. The other thing is basically how many processes you use for IPC management, right? Which you can change, of course, yes.
Okay, thank you.
I have, yes, one question, maybe last one, because we are running a very long time. One question. If you deploy in memory, directly in RAM memory, you have deployed for memory, no? Basically. How do you define the size of the container per server? I mean, you have to say something. I mean, you do it by configuration, you have a static, you allow dynamic greedy allocation. I mean, how do you define this parameter without affecting the application running in the node?
You mean the amount of memory that GekkoFS is using, the daemon?
Yeah.
Okay, well, here's the thing. In this example that I was showing, I was just using the memory as data storage. Of course, you would normally do it on the SSD, and then what you will have is just the kind of kernel caches that I used anyway. But we're not using memory really for that. So there's not really a problem there. But if you would use it in memory, of course, you will use it until the memory is full. Like if you really want to store the data in memory. We currently don't have a way of restricting that. You will notice it when it's full, basically.
You mean that the system can be greedy and consuming all the application, all the memory? Yeah,
we don't have any boundaries. But again, it shouldn't be like you can run GekkoFS on memory because it is a path if you have a TempFS or a RemFS or whatever. Okay. But it's not really the use case. Yeah.
Mm-hmm. Okay. So thank you very much for the presentation, Mark and Ramon. I think it has been very, very interesting. So remember that for all the attendants that we will have the video recording on on the web page of the project, and that will be open for everybody. So you have more questions, probably you can do it directly to Mark and Ramon. The idea is that we have is to the proposal is to use GekkoFS system in the project. So all the use cases should be at some point running on top of the GekkoFS system, considering not only the physical file system, but also Gecko, and use the IO scheduler made in VSC. Okay. So thank you for the presentation, and see you for the next webinar. That I don't know I don't remember the date, but probably it could be in 1 week or in 2 weeks. Okay, related to applications. Thank you.
Thanks you for having us. Thank you for the questions. If you are an admirer, please, if you set up and you have problems, send us on Mattermost a message. And if you're not an admirer, send an email. We're happy to help.
Okay. Thank you. Bye.